Get wired up. Good. Okay. This is a short presentation. I'm going to make room for some of the other speakers in this group, so I'll breeze through this pretty quickly. But this talks about a notional idea. It's not committed to yet, but for an on-orbit cross-calibration radiometer, not unlike what you've heard with truths, others. Background, yeah, there's been a radical growth in remote sensing. Over 300 Earth-observing satellites have been launched in the last 3 years. It's actually in the last 2.5 years. Moving from data scarcity to data abundance. How do we use so much data? That's why we're here. Harmonization, how do we get it together? And there's many data characteristics, many challenges. I don't know if it's calibration, is it harmonization, is it interoperability? I wish somebody would define those words for us. But there's definitely a need for common references and then the standards that we've talked about. The common references and practices, geometric and geodetic calibration is actually one of the easier things. There are many methods of doing that. There's also some good base maps out to begin with, although we do need some higher res ones, as was mentioned earlier today. Spatial and sharpness measuring, that's probably the easiest. If you've got the right image, there's a lot of tools out there that can help you quickly characterize your system and understand how your system's performance is. I'm talking about on-orbit right now. Radiometric on-orbit calibration is difficult. It typically involves field campaigns, which only provide 1-point measurement. You've heard some of the difficulties of that earlier today. Or the use of PICs or lunar calibration, each of which have their own uncertainties and troubles with those. All of them have some limitations. RadCalNet is a very promising thing that's coming up, just starting right now, but again only provides a point measurement. And spectral calibration, that's only done on the ground right now. We don't know how to do that from space reliably and easily. So what we propose, a notion that some of us are kicking around, is an on-orbit cross-calibration radiometer. It's highly calibrated, perhaps not as exquisitely as Truths or the proposed Clario mission, which I think was 0.15%, amazing. But with good calibration on orbit, we should be able to get this down to 1% goal. Hyperspectral across the whole V-sphere region, and we're choosing to have 100-meter GSD to maintain signal and noise. We're going to be, with the hyperspectral, slicing it into so many slim slices to keep your signal and noise up. 100-meter GSD gives you about 37 times the input radiation as a 30-meter bird. And we're looking at a 60-kilometer swath to minimize look angle issues, also to cut down on the data coming down. That and the GSD really cut down on the data, make it reasonable. And this satellite's primary mission would be cross-calibration. Secondary missions, it could build up a slow coarse resolution hyperspectral base map of the Earth and provide good high calibrated images of the moon to add to the existing Rollo data set that was gathered on the ground. This would be space-based, remove atmospheric uncertainties from that. And we'd choose a sun-synchronous orbit to maximize the intersection time. Some other systems are proposing other orbits that would give occasional brief intersections. We like to have long ones so that you can look for stability, see many different types of ground underneath there. So here's what cross-calibration does. Here's an illustration of our proposed radiometer. We chose an 854-kilometer sun-synchronous orbit. Gives a 48-day repeat. There's Landsat coming across, and then here comes the calibration radiometer behind it. This doesn't happen all the time, but occasionally, because they're in different orbits, it happens like this. This one, the area toward the upper left there would be the best because you're in the center of the Landsat portion. You minimize the look angle differences, BRDF effects, and so on. How often would this happen with other systems? Sentinel, we look at the Sentinels here, and here we minimize the Sentinel ground footprint to only consider the center portions plus and minus 3 degrees from nadir, and where those would intersect with this. You see a beat frequency happening as the satellite comes in phase with it and out. This is 1 month of intersections, and you can notice the long paths, being able to monitor stability of the instruments, of the target satellite, also seeing many different types of terrain, land surface underneath there, many types of atmospheres, being able to calibrate with that. Landsat would be very similar since they're close orbit. So we put this at a 10:15 crossing time, so it's a very similar sun-synchronous orbital plane to that of Landsat and Sentinel, and most of the morning crossing birds. How would it do with something like one of the commercial birds? This shows with the intersections that would happen. They're awfully faint. If you can see thin yellow lines there coming across, I think you can see them. But that's where the narrower footprint of a planet dove, a single dove from flock 3P, we use that as an example. And you see some long calibrations. This would be nice to monitor in-orbit stability, how the system responds as it comes through one entire orbit, heating, see if there's any temperature dependencies, things like that, and offer good control of them. Now, imagine all of the other, there were 88, I believe, birds in flock 3P. That's a lot of stripes on there. There'd be a lot of data for Planet to play with, available every month. And we just did it for a month so you don't darken the entire screen with intersections. Now, this is not a movie. That unfortunately shows what happens with the PM, an afternoon bird. That's the MODIS instrument on our intersections with the MODIS instrument on Aqua. You notice they're only occurring up over Greenland. Because that's an afternoon bird, we would never cross those parts of the orbit except up at the tops, at the top of the orbits. This one is picked during our summer, Northern Hemisphere summer. In the Southern Hemisphere summer, the austral summer, it'd be down over Antarctica. That's less than optimal, low sun angles, not a good crossing time. So to avoid that problem, we talked about maybe putting an instrument on the International Space Station, a parallel instrument with that. One in sun-synchronous orbit, one in ISS, which you can see small intersections. They don't have the long swath intersections, but you see them scattered around over both hemispheres. Again, this is 1 month. If you allow it to continue running, it adds up to quite a few. There's a beat frequency that goes with the two different orbits there. But this would offer virtually every satellite intersecting capabilities with it. Now, you may have heard that there are plans to put some very high resolution or very highly calibrated instruments on the ISS. There are also plans for Truths that we heard about today, Clario, an exquisitely calibrated mission from NASA. Why do we need to be here? Clario is no longer being considered. It's kind of on hold in the Phase A process. It was going to be exquisite, but that's on hold. Clario Pathfinder is still progressing. That will be an instrument with a 1-year mission for the International Space Station. That'd be great. That'd give us that ISS crossing that we saw. And also allow crossing back and forth between the cross-cal radiometer that we propose and the Clario Pathfinder. More references to tie each other together. The more references we tie together, the broader they cross and offer more intersection opportunities for every satellite up there. Truths, very similar to Clario. 3% traceable. It might be launched. I think it's planning to. They're expecting in November the Gathering of Ministers to approve funding for it. That will be excellent. It'll take a little while to get up there. But the CCR, we think, could be built relatively rapidly. A goal of 1% is not as good as those other two, but for cross-calibration of most of our land imaging satellites, particularly the commercial birds and so on, it would be a wonderful reference to use now. Is it possible? Yep. There's preliminary discussions happening at NASA now, looking at how this could be done, and how it could be done quickly. Choosing calibrators for it, everything. It'd probably be a small sat, most likely ESPA class, only if it grew a little You know, if it had to, the calibrators might drive us into ESPA Grande, but our fearless leader Phil thinks it definitely probably could be an ESPA class. And we'd probably do it quicker to get it up as soon as we can. There's a need for this now. And I think that it complements and it doesn't conflict with Clario and Truths if they both get up there, Clario, Pathfinder, and other. This helps extend both of their records out more and makes calibrated reference imagery even more widely available to satellites in orbit. And so now, how do you use reference imagery like this to assess your own imagery? That's Minsu's talk. I'm done.
I guess John did start an introduction, Minsu Kim. So your talk is on the conversion of the Dove and Landsat radiometric quality to Landsat 8. Right, so that'll be good, cross comparison.
Oh, thank you. I have a colleague who did mostly data processing and a lot of software work, SK Power. So I'm working at the USGS EROS, the SUFORS, as a contractor. EROS is always interested in other satellites, especially we are thrilled at looking at the small sat community advancing fast and promising a lot of much efficient and which fill the gaps that lacks in the conventional big boys. So actually I had a presentation last year just focusing on Dove Classic on only radiometric side, and also today EarthyCast presentation was very nice. So it's at the same line of thinking. So I would jump a lot of things and then show other examples on Dove-R and Dove Landsat. Also briefly touch about the deconvolution stuff. So, as you know, and yeah, basically digital number radians, it's not suitable for comparison, so obvious reason. Of course, Alan did a great job on surface reflectance, but it's not, I thought it was not available for Dove Landsat and Dove-R, so I limited to two-way reflectance. It should be least debatable. So the idea is we got 30-meter and 3-meter planet. Of course, you have to downsample it, resample it to compare. So unfortunately, you have to combine 10 by 10, 100 pixels into a single pixel to compare. So this is what we get. So each pixel is 30 meter pixel. On the left is, of course, Oli, right, is Dove Classic. So that's what you can compare for 4 bands. X-axis is Oli, and Y-axis is Dove Classic in this case. So don't kill me, but in the worst case, you can see like 100% error. But like Landsat says about 6%, but Planet says about 12%. But we all know that that's a, they can be found in many, like more than hundreds of different cameras from the Classic. some of them will behave like this, and these are not very well taken care of. So, well, that's not a problem. That's not a problem. We will go to, I mean, it's just an observation. We will try to find a way to come up with something really good, right? So usually we assume that Landsat must be the top-notch radiometric quality sensor. So obviously, Planet must be wrong. So before saying that, we can compare with Oli versus Sentinel, and it looks pretty good. So it's convinced. Anyway, so before doing that, we need to briefly take care of the relative georeferencing issue, right? So we got 30-meter Planet image there, and let's say this is one upper left Oli pixel, which is 30 meter by 30 meter, and it has a easting northing tag there, upper left corner. And obviously, if you don't care anything about the relative georeferencing, then you have to refer to easting northing number, that the exactly same easting northing number from Oli, right? And you go there and then find 10 pixels to the right and to the bottom, and you just bunch it into single number. That's what we'll do. But let's say the true location of the Oli pixel was here. So we have relative georeferencing error or difference of delta n and delta e, then that will cause problem because you're not comparing apples to apple. So it's a way of coming up to that relative georeferencing errors. In this case, through the optimization process, you got 3 pixel and 3 Oli pixel. I'm sorry, 3 Planet pixels. So actually 9 meter and 8, which is 24. The animation doesn't work, so let's pass. Okay, so I'm just saying that relative georeferencing error is critical, and it's been taken care of pretty well. So if you do not do that, and on the right, if you do that, then the blue channel, green channel, you'll see that the scatter is much thinner and less scatter, so which is essential in doing radiometric comparison. So in case of Planet versus Sentinel, because Sentinel is 10 meter, you need to have some specific consideration on that. So my strategy was, instead of getting 3 and 1/3 of a pixel, which is not the whole number, so there was a strategy I suggest, and that's the way I did. So for example, MSI and Doval, background image is Sentinel, and then of course overlaid frames are from Doval. And from one frame there, from 3 different locations, you get 0 and 2 relative georeferencing. So it's pretty good. In these cases, you got 2 and 2 and 3 and 2, like 3 and 2. In this case, 2, 4, 3, 5, 4, 5. So this algorithm is dependent on the surface type or the complexity in high frequency information is affecting that result. But roughly, it looks okay. But you know that I mentioned it later. So this is taken care of. These are showing some examples. But one specific case, we found in computing the relative georeferencing, we used near-infrared channel because that's the brightest number, right? But this specific case, this blue channel behaved very weirdly, right? So, so let's simply observe the phenomena. So this is the observation that using near-infrared channel. Is it? Yes, near-infrared channel. So I got -3 and 2 georeferencing in terms of dove pixels. But this is without doing it. So definitely there is an improvement a little bit, but it's not satisfactory. But in this case, if I use blue channel for that relative georeferencing evaluation, then I get quite different number. Instead of 3 and 2, I get 1 and 4. So some scenes, I should say, some camera has to more careful treatment for estimating this relative georeferencing. Of course, this will be different in different part of the Earth, different time. So it's quite mess, but the methodology is here. So this is a quick example that showing, visualizing that relative georeferencing. So anyway, so this is what is observed, radiometric comparison. Now, it is obviously revealing some lower radiometric quality, let's say, lower relative to like Oli or Sentinel. Then what can we do about it? Let's say this is the observation, but we want to have this kind of correction, right? So it is of course possible. If you use simply the inverse correction approach, then the initial dove image, the dynamic range of this TOA reflectance can be adjusted to this way. So that, of course, assuming that this Oli reflectance dynamic range is right, rather right. So it has to be, in this case, smaller dynamic range has to be kind of expanded, so it's kind of showing expansion. So this R dove, raw dove reflectance, should be remapped through this simple equation, and then it creates some kind of R prime, which will be closely emulate raw Oli. So in this case, like contracted because of the simple, different slope. So this is basic approach. So this is before and after. Now what's the real tangible example? I mean, yeah, let's start from Dove Classic data set. This is one data set. This shows before and after. Inverse correction. Of course, we can call it cross-calibration. I should say that's a better term, but I simply coined this different word. So now we are looking at 30-meter resampled, downsampled image. First image is, of course, Oli TOAL. And second image was raw Dove data. And third is inversely corrected, cross-calibrated. This is typical RGB. This is force color, NIR. So this is key idea. You got Dove raw data set, 3 meter. Now, applying that, the inverse correction, cross-calibration, this is what you will get, which is much closer radiometrically to Oli. So even if you measured, your initial camera collected this kind of data set, you can, if you are convinced to this approach, you can modify Dove data set into that, which is in the same 3 meter, and then provide to the customer. Of course, this approach is generic, so you can do any kind of small set or even other. Okay, so so small set has always inherent advantage, right? It has high spatial resolution, and also very frequent revisit time, because you got hundreds of satellites. On top of that, if you add this high radiometric quality, then this is a really promising, daunting system. So that's, I think, I cannot say official USGS position, but all the project managers, they strongly advocate this approach. And yeah, so let me look at a couple of other examples. This was in Colorado, I think. This example, Banizombo in Nigeria, sorry. and another Toulouse, France. So yes, this is before and after converting. So are you doing that now? Okay. So yeah, we can take a look Doval. Now it's a little different story because Doval data, as far as I heard, it's initially go through cross-calibration against rapid eye. So which is maybe not as good as Landsat, but respectable. Because of that reason, if I do the same thing, Doval versus Sentinel, this is what I get. It is good already, because if you look at the spectral slope, the slope in the comparison, it's almost same slope as 1-to-1, right? So slope is what matters. Of course, there's an adjustment in the brightness magnitude a little bit, but so this is very good. Australia data set, of course, in this case, almost perfect, so we don't even see any differences. Dove Landsat. So it's a good news for Doval and Dove Landsat, which is a single satellite, but we observe pretty same thing. There's offset, but slope is almost identical. So the before and after, we don't see much of difference. So this is a well-maintained, well-calibrated, relatively compared to Dove Classic. Yeah. Now, let me briefly touch about that point spread function issue. Sorry about that. This is about universal correction. So basically, this is an example with Dove Classic. Dove Classic has hundreds of different, less than 200, but many, many different cameras. So these data sets are from different cameras. So as you can see, there's no consistency in the radiometric behavior, right? So for example, red channel has this slope, this offset, but the other camera has this, the other camera has that. So you got these issues. So the point is you have to do this inverse calibration, cross calibration for camera by camera. That was the point. And to do that, in this case, it's Dove Landsat data set. So you go through many, many different parts of the world and from different dates, starting from September, November, and December, you collect all those data sets from many different areas. So now you can get the universal inverse formula. So obviously we have an issue with the desert data set from, this group is desert data set. So if you exclude that, then overall you have very nice consistent radiometric characteristics. Of course it's Dove Landsat, which is a single unique camera. But Doval, you have to do it separately for each and every camera. And testing, using that universal formula, you can just apply it to other data set which was not used for that universal calibration. It looks good. Of course, I'm not showing the image. If they are aligned 1-to-1, then that it's guaranteed to have almost similar looking data sets. Yeah, we saw several images, but regardless of Dove Classic or Dove Landsat, Doval, consistently we observed that the fuzzy, blurry image all the time. So we thought there must be something we can do about it. And it's a zoom in of that portion, and this is ground truth from Google Image. So as you can see, point spread is quite severe. But of course, in this case, it's bright image against the dark background. So it is kind of like emphasized or exaggerated. But overall, point spread function is this worst image. But anyway, before and after deconvolution. So of course, the definition of these bright buildings, linear buildings, and those boundaries are much pronounced, clear and sharp. But as I said, EarthCast result is much, much better in my view. So the point is basically the yellow curve. Yeah, raw planet point spread function convolved blurry image. Let's say the red curve is the horizontal profile of the digital number. And I applied, of course, I estimated certain point spread and then applied deconvolution. So this blue curve is the horizontal profile that I came up, right? Of course, it is deconvoluted, so always convolution subdue the high number lower and then low number like higher. So that's what we initially observed, this red curve. But assuming this deconvolution was pretty modestly done, then we have to observe something like this. So overall, this is a good approach. And if the original data set is problematic in terms of blurriness or fuzziness, then you can obviously apply this approach. And the intellectual property by EarthCast can be adapted to much improve. So I pass the MTF. So show some of the examples more. Oh yeah, sharpening here is not the typical pen sharpening type of approach, but it's just deconvolution. So this is one example before and deconvoluted. Yeah, let me stop here. So overall, that USGS loves to see those small set data, how they improve their data quality. I mean, initially we saw very bad geometric accuracy, but it is very respectable right now. And also radiometric quality compared to classic to Landsat and Nova, it's much, much improved. Going forward, we are expecting again, the inherent advantage of high spatial resolution, and on top of that, the high revisit frequency, and you got this nice high radiometric fidelity and a little sharper, then there will be just an amazing system. Thank you.
I will make the comment that we do have an uncertainty in the Oli calibration. The spec is for 5%. The traceability calculation is just a little over 3%, estimated in terms of an absolute error at launch. So you should give yourself that kind of a wiggle room in the comparison. It's not got the full 12. So the next talk will be from Rasmus Houborg. He's going to talk about the CESTEM Data Cube release of the harmonized surface reflectance products over targets from regions in California. Thank you.
Do you mind if I make it nearer?
Great.
Go back to the same tablet. Which tablet is that?
There we go. All right, thanks. So this is about data harmonization, and this is about kind of the first look at some of the harmonized data product that we are offering at Planet. So this release specifically is about data cubes over California. And really the objective is to give a first look at the data and maybe foster investigation into the potential benefit of using harmonized data stacks for doing science, for doing change detection and time series analysis and other applications that might benefit from this type of data. So it's really about kind of exploiting different data sets from different sensors. Obviously, we want to make the best out of our satellite constellations, the Planescope satellites. But we want to bring in the public data source like Landsat and Sentinel to kind of enhance it in space and time. So there's both a harmonization aspect. So we want to make it look like the gold standard. In this case, we're using the harmonized Landsat and Sentinel as the gold standard. So we want to make our data look like that in terms of the radiometric calibration. So we're doing a radiometric normalization, but we're also doing a data fusion. So we want to enhance the data also in space, producing a seamless daily product at 3-meter resolution. And then we're doing a lot of validation as well. So we're also looking at how it compares with ground observations to ensure that it has the needed accuracy to really do science and other cool stuff with it. So it's kind of a high-level analysis-ready product that has been cleaned up for clouds and any calibration issue you might have. So this talk I will mostly about presenting some examples, less about the actual framework and the methodology. I could spend a full day just describing that. So just briefly go over the methods of the framework. So basically, as I mentioned, it's about exploiting the high calibration, radiometric calibration of the gold standard satellites like Landsat and Sentinel, but then also at the same time exploiting the added benefit of a CubeSat constellation like the one Planet has in terms of the spatial and temporal resolution. So it's really about bringing these data sets together, synergize the individual benefits, and produce an enhanced product. So the methodology is quite evolved and quite complex in many ways. In terms of the basics, it's really about drawing reference data from your gold standard satellites, being the HLS dataset in this case. So really, for any planescope scene you have, you need a corresponding reference image, and you are kind of deriving that reference image from past collections from either Sentinel or Landsat data. So it can be, in this case, I'm showcasing 5 past kind of scenes, but it can go even further back. It can go back a full year. So you're kind of working with a deep stack of data, and you're kind of drawing data from that stack and using that as to establish a reference data set for each of your planescope scene acquisitions. So the calibration is done independently for each scene. And that means that you can input anything into it. It doesn't have to be a highly calibrated image. It can be digital numbers. It can be anything really. It doesn't have to be calibrated. The association, the machine learning technique that is used will ensure that the output is consistent with whatever reference you choose. And then as part of the calibration, we're also using MODIS data. So as things change when you go, away from your day of interest, there can be change occurring, and we're using a MODIS consistent planescope data archive to kind of assess that change over time and to derive a good reference image for that particular scene. And then we're also doing scaffolding. So after we do the calibration, we produce the harmonized product, we then apply some scaffolding techniques to create this daily product. And that scaffolding uses MODIS data as well as past and future past planescope scenes to kind of fill gaps in the data and produce that scaffolded product. In terms of actually creating the association, translating, so we're inputting the planescope top of that reflection, so that's the input. So we want to get that to look like an HLS consistent surface reflectance. And for that purpose, we use a cubist regression tree approach to kind of establish that associations for each individual scene. And that's kind of visualized here. And then, so this is, you have your inputs, which is the top of that reflectance. You have your reference, the HLS, and then you get your corrected output, the system surface reflectance. And you can see that after the correction, you get a more consistent looking NDVI in this case. That is quite similar to what you get from the HLS. This looks more into detail in the actual calibration. So it looks at the gain factor. It's basically the multiplication factor that you need to multiply your top of average reflectance to get your system surface reflectance output for this particular scene This is just one scene in 2018. And this kind of shows you that for the red band, you need to, in some cases, over the dense vegetation, you need to multiply your type of reflectance with around 0.4 to get something that looks like an HLS, like red reflectance. But as you see, it's spatially variable. It really depends on your vegetation conditions and your vegetation density. And it's very different. It depends on your band as well. And it changes from day to day. So this is just another day. It's quite different, both due to changes in your cover conditions, but also due to changes in the satellite. It's probably a different satellite on this day. They might have a slightly different spectral response. So the algorithm is also trying to take that into account. It can work with satellites with completely different spectral responses. It will still produce the same kind of output. And this is just to kind of exemplify that. So in terms of the data cube, this is currently the list of AOIs that I'm working with. This can be expanded, but this is just meant as a first look. These AOIs were selected based on existing instrumentation sites. So a lot of them have ameroflux towers, they have phenocams installed, and other kind of ground measurements. So if people want to kind of compare it to existing measurements, these are good places to start looking, but I'm open to expanding it to other sites, should that be of interest to certain people. In this talk, I'll just kind of demonstrate a few results from the Angel AOI, and the Imperial Valley, two cropland sites. So this, in terms of the products that will be available in the data cube, so there will be the input data set, the planoscope, top of atmosphere reflectance. You will have the HLS, the Landsat or Sentinel 30-meter product in the data cube as well. And then you will have the corrected system surface reflectance product, as well as the daily gap-filled surface reflectance product. And then it will give you the data cube. So I'm looking at a time period of 18 months for each of the AOIs. So you get a stack of images over that time frame. It will look something like this, just for 1 year of data. This case just showcases how it looks for the green band for a particular pixel within that AOI, showing the regional planoscope data in green, and then you corrected, in this case, the daily gap-filled product output, along with the Sentinel and Landsat output. So this is what you get, these deep stacks for each of the AOIs. And this is just a near band for that same pixel. And this is the Angel AOI close to Fresno in California. So in terms of the processing, I do chunk it up to speed up to handle memory management. And this is just one of those chunks. So you can see that in this case, it is a combination of two planoscope scenes. So it will merge whatever scene is available. I think this is probably a Davar. This is in this year, in May. And this is how the data look. So this is the input, the planoscope top of atmosphere reflectance. It's a bit cloudy. So STEM also includes techniques to remove the clouds using both scene-based and temporal approaches. So it kind of exploit the deep stack to kind of remove the clouds. And this is how it looks for that same kind of chunk. So you have the original data, input data, and then your calibrated output data that has also been gap-filled and produce something that looks like a good high-quality image. And then you move to the next chunk, looks something like this. You top of atmosphere reflectance, and this is the STEM output product that has been gap-filled. And then you can kind of work through the full kind of chunk. This is in general quite cloudy scene, but you end up with something like this for the full AOI, where you have quite contaminated input data, but you're still able to get something that looks quite good as an output due to the gap filling routines and the ability to detect the clouds with a decent amount of accuracy. And this is just a zoom in on one point where you do have a lot of contamination and kind of high cirrus clouds that are usually quite difficult to detect. But in this case, it is successful in detecting those and producing, kind of reconstructing the surface below those clouds. And this is just another example. It's a quite aggressive cloud detection technique, and sometimes it does remove more than than necessary, but it's kind of the approach that I've taken to that it's better to remove more than too little. So in some cases you will see some commission errors, but in general that is beneficial for creating a gap-filled final good-looking output product. Yeah. And this is just one moving, I don't know if you can see it, but this shows the original data as input, and then you have the system corrected data. These are RGB, and this is your NDVI. And you can see, kind of get a feel that sometimes you have a contamination that you don't see in the final output. In some cases you do see some artifacts, but in general it's a fairly cleaned up product that should be quite useful for doing time series analysis and detecting change with high fidelity. It runs through a full year there, so I'm probably just going to stop it here. But I will upload these as part of the release, and they can be accessed as part of that data release if you want to have a closer look. And this is just a closer look at one specific pixel within that AOI, looking at each of the bands, the green, red, near infrared, as well as the NDVI. And you can then see how, in terms of the temporal consistency over that specific AOI, and you do see some noise in the original data that is mostly removed as part of the system calibration approach. And you also see that it is quite consistent with the HLS datasets. So this is a fairly clear site, so you do have a lot of HLS data, as you see. It's quite good frequency of the Sentinel and Landsat data. But in some cases, we do have a significantly better revisit by the PlanScope satellites. So Imperial Valley is another of the AOI that's going to be available. Again, showing one of the chunks and the input data, and then the calibrated output. And again, pretty good in terms of removing the clouds and producing something that looks quite good. And this is the full AOI for that particular day. And then when you kind of zoom in this case, you also kind of see a seam boundary in the original data that is not visible in the corrected data. So it will attempt to remove those kind of scene-to-scene artifacts as it does the calibration on a scene-specific basis. And then again, a movie kind of highlighting the utility of the daily gap-fill data to produce good data. And you can see there's a lot of things going on. So this is really kind of a dynamic site in terms of vegetation dynamics. There's a rapid growing cycles. And occasionally you see contamination in the original input data that you don't see in the output data, in the calibrated output data. So that is what we want to have, like a really cleaned up product that is useful and readily useful for doing analysis and as input to various applications. And then we can go into a particular pixel, or in this case a particular field, and look at the time series. And then yes, you do see that this is a really, really dynamic vegetation site with multiple growing seasons over 1 year. Again, at the bottom, kind of highlighting the NDVI dynamics for this particular field, and the ability to quite accurately kind of track the growing cycles. And in this case, sometimes you do see quite significant gaps in the HLS data record, where the PlanScope data add additional benefit. And this is, so this one is just the regular data product, but this is the gap-fill. So it will kind of fill the blanks that might exist in the original input data sets. And when you look at one period of time where you have a gap in the Sentinel-2 record, so there's actually a 16-day gap in this case. So we have a Sentinel-2, HLS Sentinel-2 on day 201. We have another one on 216. But you're really missing out on the stuff that happens within that period. So you're not able to capture the exact timing of the harvesting. and any kind of subfield variations that might occur over this 16-day period. But you're able to capture that with the planoscope, with the calibrated planoscope data set. In addition to kind of having a high spatial resolution that can be beneficial in this kind of for field scale studies. So there's three additional AOIs as part of the data release. I will be posting access information on the ARD website soon after the meeting, and I will have additional details on the data format and the structure of it and how to access it, and then we're just hoping to get some feedback and ways to kind of improve the data delivery and the data format maybe, and just getting feedback to improve it even further. So I think that's what I have, and I will leave this as the last slide.
Okay, we're going to bring our speakers up. So one of the questions I'd like to put out to the three speakers is how much. One more. Oh, we have one more speaker. I'm sorry, I didn't mean to cut you off. It was none of the program.
Yeah. So this is Adam Wolf from Arable, who was going to present tomorrow, but is going to present today as part of this block. Let's try to keep it in their time because we have to pack our panel.
Can you hear me? Okay. My name's Adam Wolf. I'm the founder, now chief scientist of Arable Labs. I, just by way of background, did my PhD mostly dealing with BRDF effects of MODIS, because my goal was to be able to take basically daily MODIS data and ingest it into a land surface model so we could do kind of global change modeling, photosynthesis, water use, whatnot. But at that daily level, had to really deal with BRDF, atmospheric contamination. This is like a bunch of multiple angles. And, 2010 or something like that, I handed off my dissertation. I thought, I'm so done with satellites. The issues that I was facing, one was that the data was coarse, B, that it was noisy because there's that whole atmosphere between us and the ground. There was all this multiple angles. The weather data that we were working with was also super coarse. And what I was trying to understand as a kind of plant scientist by training, I thought, well, what if we start developing things that are closer to the ground and kind of directly monitoring the plants? And so I'm going to be kind of looking at this from the perspective where Rasmus was looking down from space down here. I'm way down here, and I'm a little bit oriented towards this device we sort of invented and commercialized. So I will be talking about the harmonization about this thing, but a lot of what I'm trying to do is to leverage the satellite to extrapolate what I'm doing. Even though I'm going to entrain you into the idea that we can use these ground instruments to be kind of tethering from satellite radiometric correction to the ground with this thing. So this is the device. It's probably 7.5 inches across. That kind of membrane across the top is actually a thin drum head. It's about 1 millimeter thick of polycarbonate, and as raindrops hit it, it makes a sound. So there's a microphone in there. It's measuring the rainfall. The fancy word for it is an acoustic disdrometer. Really what's kind of relevant for us here is that little smile at the bottom is, it's actually a 7-band spectrometer and a radiometer. And there's a little lens off to the side that has a thermopile in it, so we're measuring long-wave radiation. So we have that pair or that set of instruments pointing up as well as pointing down. And so one of the goals is to measure reflectance. So combining, basic measurements of weather with, well, what are the plants doing in response to that weather? Another sort of obvious application is net radiation. Drives a lot of important plant processes. So that's upward and downward shortwave and long-wave radiation. And then the downward long wave is, of course, the canopy temperature or the radiative temperature of whatever it's looking at, and that's used for a variety of things, including like plant stress, but also detecting leaf wetness and condensation, things like that. As far as sort of the CalVal, why should you trust this thing on the ground? Each one of these is factory calibrated with a NIST traceable lamp. And then further, that's sort of a unit level calibration of the sort of each individual sensing element within the device. And then these are deployed at 25 different sort of reference calibrated sites. One of the more important ones is National Renewable Energy Laboratory that has a completely badass set of radiation measurements, as you would guess, including spectrally resolved measurements. So I'm not showing you the calibration against that, but we've got strong shortwave calibrations as well as spectral calibrations. And then we use the DOE ARM site in Oklahoma for our upwelling radiation calibration. So these guys are all over the world. There's on the order of 2,000 of these around, and you won't be shocked to see that the majority are in the US and Europe. It's mostly limited by connectivity, not surprisingly. And one of our first applications was taking the weather from this and having downscaled weather predictions. So understanding the anomaly of this peculiar little valley versus what the National Weather Service thinks is the weather, and correcting for those anomalies. And in the same way, we'd like to do this for satellite remote sensing for kind of color correction, let's call it. So our major research threads, one of the main ones is value-added data streams, so evapotranspiration, gross primary productivity. There's, as I described, a predictive analytics piece, but also the spatial analytics. So how do we leverage the measurement at this point to say what's happening in the next field over? And so we spent a lot of time benchmarking whatever we measure against some empirical version of the truth. So one of the motivations for this talk was, came to me via a mutual collaborator. Originally, the data points on this were collected by Rasmus. And this was 2018, so somewhere around August, we're looking at the soybean field. And it had always been kind of hanging out in my mind to do image fusion work, and this kind of pulled it all together, where on the one hand, Landsat may be high quality, but it's completely absent from when those times that are fast changing and therefore people need to make decisions, okay? And it's actually not totally surprising that when plants are rapidly growing, they're taking a bunch of water from the soil and putting it into the atmosphere and causing clouds. And so these things are kind of correlated to each other. The inability to look at the ground happens when plants are rapidly growing. And then this was not the CESTEM corrected data, which looks beautiful, but this kind of raw image or the raw data points from the uncorrected planet data. So we looked at this and thought, okay, what I want is to be able to have a synthesized data set that allows for this kind of continuous set of corrected data, because on that middle line, which is data that we collected, you can do time derivatives. You could do real calculus on it to infer all kinds of things, like when is that peak going to happen? And that's probably related to flowering, and we might want to do something around that time. So a lot of analytics comes out of being able to directly compute day-on-day changes. So I'm going to look today at, this is just a beautiful, nice curve, boringly beautiful, but I'm going to show you a much crummier set of data collected in the Napa Valley, which, if you're not from around here, it's just about 150 miles north of us, up in the northern end of the valley, and there's that field right there. And just for reference, this is why it kind of sucks. You've got a device up here, and from trying to understand what's going on in the ground, the thing you care about is all stacked up in the middle in those trellises, the vineyard, and yet there's all this other stuff in the middle of the rows, which is the cover crops, and those cover crops are kind of a fact of life for vineyards. They're used in part to deliberately dry out the soil. And so one of the real challenges in interpreting this data is the separation of the background from the foreground. I'm not going to overly worry about that for this talk. I'm just going to say we care about all of these sensors giving us a sane, similar value. So set up the experiment. This is what we measured, and this ends, just a couple days ago. And you could see on the bottom plot, the yellow lines are rainfall. And I apologize in advance. Every single label here is going to be a little bit too small for you to read, so I'll try to narrate it. So we've got a bunch of rainfall, and not surprisingly, when it rains, it's cloudy out. And so the blue line that you see is the actual divided by the potential radiation integrated over the whole day. And without making your eyes do this, whenever it's cloudy overhead, there's a little bump in the reflectance. And what I'm going to be plotting here is not the raw reflectances, but the NDVI. And the actual reflectance does change because between direct and diffuse light, the canopies absorb more or less of the radiation. So it's a real phenomenon, but it doesn't relate to how much plants there are, which is kind of the thing that we care about. And want to be able to detect stuff like this, like that is a pruning event. In other data sets, you can clearly see the cover crops being mown. If this season was further along, you'd be able to see senescence and eventually harvest. One of the things to look at that's really interesting, January 1st, we have a clearness index of 0.7. So, the maximum value at the South Pole, actual over potential, you're like in 0.7, 0.8 territory. So an exceptionally clear place, you only get 70–80% of what the solar constant is. And what do you see over the course of the year? That's California, which is bad air quality. You see this especially true when there's fires. So the clearness index over here is 50%. And so everything that you see from that decline is stuff in the atmosphere getting in the way of the sun reaching the ground. And so one of my goals in this talk is to be able to sort of deal with that. So what did we get from Landsat and Sentinel? That's at top, the raw data coming out, and then just kind of doing a dumb filter of throwing away everything with the NDVI was below 0.4, we get the top line. So I'll show you in a second, it's quantitatively similar. The difference between these two is 0.073. So that's one of the questions of this talk. Why is there this almost 0.1 difference in NDVI? That's a substantial difference biologically, so that's meaningful. And it's actually systematic. That's kind of funny. And then, well, how do those in turn compare to what we measure on the ground? Well, at the early part of the season, we seem to be tracking, the labels are wrong here. The orange lines here are Sentinel, and the more occasional blue lines are Landsat. So we seem to be tracking Sentinel in the earlier part of the season and then kind of tracking Landsat later in the season. Some of these phenomena that we see, like this little hump over here and then the increase before drop at pruning, we see the echo of that in the Sentinel data. So there's some signal there that is real, and yet there's that discrepancy. So we want to understand, well, why are those discrepancies there, and can we get rid of them? My goal is physics, but I'll resort to brute force if necessary. What are my goals? One is I want to create a flag to remove uncorrectable images before I bother downloading them. Okay, so if I know based on what's on the ground that there's a shadow falling on the mark the moment the satellite passed overhead, I'm not going to bother trying to download it and service it to a customer or whatnot. A lot of this is kind of done on the fly, but probably the larger goal is to take whatever is left over, which is most of the images in this case, and correct them to a common baseline. And so the rest of the talk, I'm going to be digging into these mechanisms of sensor disparity. One of them is near and dear to my heart, which is BRDF. The other is another is the spectral response, and finally getting into atmospheric correction. So as I said, we've got an upward pointing spectrometer, so that should be able to tell us something about what's between us and the sun, basically. And just kind of in the spirit of this workshop on supplying images that have all the other attendant data to use with them. I couldn't have done any of this stuff if the images that I got didn't also have the annotation of all the geometry, the time it was collected. I probably didn't need the microseconds, but they were there. The spectral response functions, all that type of stuff. So here we are with the BRDF. So we have this kind of fun model, the Ross thick, least sparse BRDF model. It's a 3-parameter model that was constrained by the Polder instrument that was up in the 90s. And so I had always been used to looking at things here, which is imagine if the sun is at this peak, and this is kind of a motocentric view of the world. What if your view angle varied considerably. So you're sampling as a satellite somewhere this function, and that function, if you get close to the hotspot, changes rapidly. And especially over the course of the year, it varies considerably. In our situation, the view angle isn't exactly in the same place, but it's pretty close to nadir. But the sun angle is changing over the course of the year, okay? And I'll show you exactly how in a minute. And just to be clear, how does our mark work? It's integrating over that whole BRDF, all right? So it's got a hemispherical diffuser, so it's measuring the reflectance from all of those angles. Under diffuse light conditions, it's also integrating light over all the different potential illumination conditions. So I alluded to this earlier, that cloudy days have a literally different reflectance. It's because we're averaging over that bowl, okay? And the average of that bowl shape is higher than, the center of that bowl shape, I'll say. So anyhow, so let's look at this BRDF function on the right and see what the impact is on these two different satellites. So these kind of dots are Sentinel and the pluses are Landsat. So there's, I'm not the expert in any level on Sentinel, so somebody will tell me this is obvious, but there's essentially two different modes of view, this view and this other view. Both of which are sort of, the sun is low on the horizon in the winter and it's closer to the center. If the sun was in the exact center, it would be at the 0, 0 point. And Landsat kind of has a similar pattern creeping up on it. And the response function we're looking at is not the reflectance anymore, but the NDVI. So here we have variations in the solar, just for ease of interpretation, the elevation angle. So it's low on the horizon up to this peak. This is all simulations, right? So the NDVI notionally that's driving all this is 0.8, practically, well, it's 0.077. So the maximum difference, even though the reflectance changes 10% over the course, the change in the NDVI is super trivial, right? So BRDF can't be the reason why these sensors are seeing something different. I mean, you could tell me there's something about BRDF that's not captured in this model, but I'm arguing that, at least to a first approximation, our princess is in a different castle. So let's look at the sensor spectral response. Okay, so here are our kernels. Here is the Landsat spectral response. Here's the Sentinel-2 spectral response. And I'm actually just going to simplify that so we can look at the same colors. So we're quite a bit broader. I think it's most relevant for this talk, the breadth in the red. But what I did was take a model called ProSail. ProSail combines two models. One is called Prospect, which is a leaf. If I tell you how much chlorophyll and pigments are in the leaf, the model tells me what the leaf reflectance looks like. And then if I arrange all those leaves into a canopy, we can sort of simulate what should the satellite see. Okay, and so I convolve those with the spectra and look at the reflectance and the NDVI. So what kind of effects should we have? So here you can see notionally kind of the center lines of each of these spectral response functions. Here is how they change as you increase leaf area. So okay, that should lead to a bias at high canopy cover. We should see a slightly lower NDVI than either of these satellites. It turns out because we're slightly capturing this red edge. But it doesn't say why should Landsat be biased higher than us sometimes, and why is Sentinel biased below us sometimes. So I don't think this is an explanation for what's causing that sort of noise and variation. So here we're looking at atmospheric composition, and just to, let me see what the plot is. Just to set up this experiment, I took the exact moment of the satellite overpass. I collected all the data from the mark, and this is sort of we have 5-minute time resolution. Joined them on, basically rounded the time together to the nearest 5 minutes. You know, maybe 10 minutes is a better rounding period just to catch passing clouds and whatnot. But basically, I was looking at in what way are those anomalies, those errors, correlated with stuff we're measuring on the ground, okay? Can I see a cloud passing overhead? So in general, looking at, bear in mind, I threw away the data where it's obvious that a cloud is directly overhead. So we're looking at more subtle changes. Really, the area where we're getting some signal is this clearness index. So how much radiation are we getting at the ground relative to the potential radiation? So this is kind of testifying to the atmospheric contamination, seeing it a bit more clearly in the Landsat data. The sample size here, anybody is free to argue that it's too little, but again, being able to look at one site kind of helps to unpack the flavor of the error a little bit more so that we're not looking at it randomly. So, you know, where did I get? I was able to cross off the BRDF effects. I was able to cross off, I think, the spectral response function effects. I believe that there's still some direction to go with the atmospheric contamination. So we made use of, NREL has, you know, the official model for solar radiation, extraterrestrial. So we're able to get a lot of leverage for a lot of applications of this potential radiation. And so one of the efforts right now is implementing, you know, what kind of radiation are we expecting at the top of canopy? So being able to get more quantitative with that, but also it has to be said that spatial help me out here. Spatial resolution is quite possibly an agent of, you know, why are these systematically different? It could be that, you know, fundamentally Landsat is capturing, you know, something a little bit greener than we are, and Sentinel is fundamentally capturing something that is a little bit browner than we are. And those footprints just happen to be different and in a systematic way. So, you know, it could be that the best we can ever do is just to say, okay, well, the footprint is different, so let's kind of brute force correct this image so that, you know, it's smoother, but we don't get that satisfying, you know, physically based, you know, correction. So I couldn't have done this without quick and easy data collection from Descartes. And I've got collaborators, most relevantly the people in whose field this is collected from, as well as some researchers who helped out with some of that. So thank you.
Let's have the speakers from this session come to the front. We're going to run probably about 10 minutes behind and catch up with the panel. So I think it will be great to take questions. This is a very thick session. Yeah. So, Phil, first. Okay.
that I run very behind.
Yeah, I'll take it to the panel. Okay. It's this one. You need it on the panel.
Oh.
I just want to reiterate some rules of engagement. Keep the answers short and to the point. Keep the questions short and to the point so we can pack a lot of bandwidth and content here, please.
Okay, so since we have people with microphones, go ahead, Bruce.
This is more in the line of a comment than a question. We talk in harmonization about 3 dimensions most of the time, spectral, spatial, and radiometric. There is a 4th dimension, and it hasn't even been mentioned here, so let me mention it, and that dimension is polarization. Now, when you're talking with planet data, and maybe Landsat, and maybe Sentinel, I'm not sufficiently familiar with those to know for sure, you may be able to ignore that plane, that dimension. When you're talking about working with VIIRS, MODIS, and AVHRR, you may not ignore that. AVHRR, maybe you can just handle it in your uncertainty budget, but nobody does. But you can't just handle it alone in your uncertainty budget for MODIS and VIIRS. You must include your polarization effects. Right now, none of their published data sets for any of those products, the level 1Bs, the calibrations, include the polarization effect in it at all. So it's not an easy problem, but it does need to be attended to. Thank you.
Okay. Go ahead.
Okay. Should I switch it on, or is it a little battery?
On the side? Switch microphones.
Yeah, that battery is, it's a long day. Question for the last speaker. Sorry, I forgot your name.
Adam.
The difference between Landsat and Sentinel-2, couldn't that be at least partial because the atmospheric correction is done with a different program, like Sent2 Core is different than LEADAPS?
Maybe, these are top of atmosphere, and so
Okay.
and
Right.
we're
No.
kind of bottom of atmosphere. So my impression is that those are not atmospherically corrected.
Okay, that's a misunderstanding from my side then. And then question about the system thing. Is this also possible to do this fusion and gap filling like near real time, or do you need at least like 1 week in the future to get your gap filled time series?
I mean, our goal is within a day, ideally, maybe within a week, but it certainly doesn't need to be right now. Get the bad guy kind of real time. But
Yeah, for the system approach, the gap filling works better if you have data on both sides of the
Yeah, of
day in
course.
question, but it can work with just having 1 or 2 days ahead of it. But in terms of the regular system, non-gap fill, that can run quite close to present. It depends. It does depend on having MODIS data available,
Right.
but that's available in near real time.
Yeah.
The ASLS data doesn't have to be near real time. You can use past collections to kind of use as a reference. But yeah, the gap filling will work better if I had at least a couple of days.
Okay, thank you.
So I wanted to make a comment about the spatial aspect. Both sensors, Sentinel-2 and Landsat, your Nyquist is pretty far down on the optical MTF. And so if you're seeing comparison on the pixels, if you're not taking that into account, that may be, like you say, part of the error that's not being accounted for.
and you can even see this kind of oscillating.
Yeah, you're mixing in things in the scene that you're not expecting when you're looking at a pixel. Go ahead.
A question for Rasmus. It's quite amazing to see the subfield pattern of, when you gap fill the data on the subfield. actually you see that evolution across time. So my question for you is that if you have a cloud, and you mentioned about masking the cloud out, where does that information come if you have fields which is on that day is under clouds?
Yeah, so it comes from a combination of data sources. So it uses the MODIS daily product as one input source, and then it uses data from past Planoscope acquisitions, or future. So anything within a certain time frame of your day in question, it will use that to try and fill the data, and it will collect as much data as needed to fill it robustly. So, but it's a combination of Planoscope data during clear sky days and the MODIS daily data.
So how does the image look like? Does that relevant to the size of a cloud in the image?
Sorry, can you repeat that?
Is the outcome that you see, the reconstruct the image, does that relevant to the size of the clouds that you're trying to gap fill using all sorts of information?
Everything will be kind of sharpened to the Planoscope's resolution. So even the MODIS data will be unmixed as part of the gap filling process.
Yeah. But how about the size of a cloud? If you have a pretty thick, big cloud, what is the threshold that the algorithm will work better, the algorithm will work worse?
Well, it can gap fill any size of cloud. Even if you don't have any scene collected for half of your AOI, it will fill that using data from past scenes and MODIS data in combination. So it will work equally well irrespective of the size of the gap,
Okay.
I think.
Okay, thank you.
If you have a lot of clouds, it's going to be more tricky, obviously. But
For sure.
Yeah.
Thanks.
I have another question. One of the things that shows up here, in fact, I went ahead and had the different spectra for the different instruments put up. That's being taken into account in, like you do the normalization for radiance. But there's a component of that assumes you know the spectra of the target at top of atmosphere. And I was wondering, how much do you think that that's contributing to your errors, that lack of precision on the comparison of the targets? Because even in the case of just picking fields, you potentially have a different spectral shape through the pass bands. Have you done any analysis?
Can you reframe the question? I think I know it, but I want to hear the question again.
The radiometric normalization to harmonize the radiance at the sensor takes into account the relative spectral response of the sensor, which kind of gets back to how much do we pre-launch calibrate, and also the scene spectral radiance, because it's a weighted interval, right, of the pass bands, and you do the ratio to try to pull the gains in line. And I'm wondering how much the lack of knowledge of the scene spectra is contributing to the errors in your comparisons. And that's true across the board. And it kind of gets to John's presentation about the transfer radiometer, the hyperspectral.
That would have to get into how the top of atmosphere calibrated product is, which I never spent a lot of time correcting a whole scene, so I couldn't really even comment on that.
Yeah, it kind of gets back to a requirement for any kind of transfer radiometer. How much do we have to characterize the target, not just the instruments? Next.
I just wanted to just segue on your point, which is if you want to convert data from one instrument to the other with spectral RSRs that are not a delta function, the problem is underdetermined, right? So you don't have enough information. You need to know the color of the target. So any tricks you play include some machine learning, land cover prior of what it is, and hence the need for calibration transfer radiometers that are hyperspectral in nature. So you can actually, you do need essentially daily hyperspectral low res to move data from between instruments. It's unsurmountable mathematically, right? It's underdetermined. So, and that's a really good point. And in a lot of the attempts we have at making harmonized data, we have lurking the color of the target underneath the, the perceived, precision or lack thereof in the analysis. Does that make sense?
The And if you're looking for global corrections, there's a lot of interest in fluorescence instruments that are very high spectral resolution, even as they are low kind of horizontal resolution. And so those in particular may be able to give you the kind of spectrally resolved ability to pull out features that you're looking for at a kind of scene level correction.
Can I go back to the gap filling question, which I think is a wonderful methodology, but it's something that the remote sensing community is not very familiar with, and they're likely to think of it as a dodgy practice in some way because they're not really good at understanding temporal interpolation. But so the question is this: it's quite simple to set up an experiment where you synthesize a gap and then compare the results. And have you done that? Surely you've done that. And how accurately is your gap filling working in most cases?
Yeah, that's a good suggestion. Something I need to do. We've been comparing the gap fill product against independent sources like Arable for instance. So, and it looks quite good. But yeah, doing like you says is a good approach. Something we need to do to verify it. But I've been busy kind of developing the algorithm, so we haven't really had time to kind of do an extensive validation.
I think the learnings from that would be a good contribution to the community.
Yeah. I have maybe a question.
I want to make one comment. He's been busy doing the hard stuff, but no time to do the low-hanging fruit, easy stuff, which is what I would have done first.
I guess I had a question for you, if I can be free to ask, which is, you know, when we've been trying to do temporal smoothing, it works well, except for the situation like we had up here where there's pruning, so there's an abrupt change. And I noticed that those fields in the Imperial Valley, those are getting harvested all the time. And I'm just curious how you balance kind of the simultaneous but opposite goals of making things smooth while also detecting abrupt changes.
Yeah, so it's not really a smoothing algorithm. Of course, the gap filling is kind of a temporal interpolation. So it will, if you have points on either side of your harvest, they will try to interpolate it, and so you get something in the middle for your gap filling, but it doesn't really smooth the data. So in order to make the data look nice, I do look at dips and peaks in the data set, but I'm only kind of smoothing it out by looking at very small time intervals. So like 1 or 2 days on either side of the point in question. So if it's more than that, I'm not considering it I'm not doing it because it could be an actual change. So I'm really careful by kind of separating out actual change from contamination, because that's a real issue, particularly in Imperial Valley where we have so rapid vegetation change. But it's a good point, and it's always going to be an issue. And the same with cloud masking. You know, you might be masking out real change sometimes rather than the cloud, because it's so similar when you use the temporal stack information to do the cloud gap filling or the cloud masking. It's a complicated thing.
To speak about that question, why we cannot just use another pixel in the tile? I mean, we look in the image, we maybe find another field that has same color, both days, the day before, the day after, and just copy paste the value in the middle more than interpolating. It may be more robust, because I suppose that when we are cutting a field, we are doing for all of them.
Yeah, I'm kind of doing that by using the MODIS data, but because it's a bigger pixel, so it does unmix that information to the planoscope resolution. But then again, using data further away from your pixel in question is also associated with a number of uncertainties. It might be the same land cover, but it can be completely different magnitude, and it's not easy doing those kind of spatial associations and still retaining the spatial features in the original data. So you can introduce additional artifacts. So I guess Star FM is one approach that kind of tries to exploit the spatial information when it does the gap filling. it works in some cases, but not always, and it's extremely computational in many cases. But definitely, you need to use as much information as you can, and using spatial information is one approach. You can also input other data sources. You can maybe input Sentinel-1 data to kind of help you with the gap filling. I think that's another opportunity, and even geostationary data. So I think you need to use as much data as possible to kind of inform the process.
Thank you.
I'm going to ask a fundamental question, and that's, do you think we need more characterization of instruments pre-launch to inform the process of trying to harmonize, where you're trying to convert apples to oranges and back?
Question for me?
That's for all of you. I mean, I know one of the the talks, you use the point spread function to sharpen, and that might get at the NTF problem actually closer to Nyquist.
Not to mention the inter-dove comparability. I mean, for us, we would be on a fool's errand if we sent these out in the wild, not having factory calibrated them. And what you're describing is, gosh, wouldn't it have been great to have calibrated those in the factory? And I think that was it already came up of just having a bunch of random calibration errors that weren't characterized ahead of time. Makes your job inordinately more difficult.
We just did the relative spectral response on OLI2 for every single pixel on the satellite instead of a subsample. So that was an undertaking.
I think the answer to your question is, well, I'm a calibration guy, so more characterization is more better all the time, everywhere. Pre-launch, yes, it will be good. I think even better yet is post-launch. Things change. Things change rapidly in the first days up there, but then you also have life of the instrument, and it's that on-orbit characterization that really matters, because that's where we're really getting the data from. And learning how to get things, having a hyperspectral system that could maybe even allow us to start understanding if there's been any spectral shifts in filters and so on. We've never done that. We always assume that it's what it was before launch. This would be great to be able to know this and understand the quality of those data better than we've ever done before.
Yeah, the question is, how are we going to back out these changes from an analytical approach looking at all the data? Now, Langley, NASA Langley has patented an approach that actually has been talked about by several groups of using tunable lasers and kind of a reference laser for the atmosphere. Oh, you got to talk tomorrow. I won't steal your thunder. So maybe we can do some calibration on orbit, at least spot check changes. Like, Veers had a change with the tungsten in the mirror. We're out of time. Okay. All right, well, thank you.
Okay, we're going to follow with a panel on machine learning ready analytics ready data that is going to be moderated here by Gopal. So here it is.
Yeah, I'm giving this to the moderator. Yes, I'm giving him this, and then you just turn it on. Yes, yes. And turn it. Yeah, it is working.
Yeah. Right.
Hello, everyone. Good evening. So the 6 of us are the barrier between the last gifted presentations and the gallons of fancy cocktails you have waiting for you in left bank. So we're going to try and make this entertaining, but there are no guarantees. I want to start with that. So I'm Gopal. I head up the team working on analytics at Planet and work closely with Ignacio and Rasmus. And I wanted to use the time we have today with all of you on this panel to transition the conversation from a focus on creation to a focus on consumption of analysis-ready data. So the panel that we have put together here is intended to be cross-industry and practitioner-centric, and that's a discussion we intend to have. So I'm going to ask each of our panelists to give a quick 1-minute introduction on what they do, where they work at, and what their interest in ARD is. So I'm going to start with Rinkal.
Hi everyone. Sorry. Good to be back, second year. So I am Rinkal Patel. I lead the remote sensing science efforts at Granular Inc. It's a startup company in San Francisco, a farm management startup company, working with farmers in US, Brazil, Argentina, and other globally different places, but heavily interested in remote sensing application towards farmer-facing questions, agronomic questions like irrigation, nitrogen, etc. Interest attending from a practitioner-centric standpoint is what kind of machine learning-related questions that we can answer from a remote sensing data standpoint, as well as what kind of process modeling we can do, biological process modeling that will allow us to better assist farmers in decision-making. Those are the primary things.
Thank you.
Yeah, hi everybody. My name is Joachim Ungar. I work for EOX. We are an Austrian-based company from Vienna. We mainly do projects with ESA, but are also involved into other activities. For example, we are partner of one of the DIASes in Europe, Mundi, which is a cloud platform for satellite data for the Sentinel missions. My field of expertise is cartography and geodata processing. Since 2015-16, I mainly was occupied with processing Sentinel-2 data. So we released 2 global full-resolution cloudless mosaics of Sentinel-2 since then. And yeah, are also reselling this refined product. So do on-demand processing of cloud-free images of Sentinel-2.
Thanks, Johan.
Hello everyone. I already gave a talk yesterday, so I'm going to be brief. I'm Alemohammad. I'm the Chief Data Scientist at Radiant Earth Foundation. My background is more in remote sensing and data science in terms of building new algorithms. I think Youngriel was calling me a hardcore scientist last night, but before joining Radiant, not now. I'm more on the applied side now. So our work is more focused on how can we have better benchmark and basically interoperable training data sets when we want to build machine learning applications. We have a focus on addressing global development applications, but all of those are shared across other countries. So we work closely with the community in terms of developing those and providing it as a service to the community.
Hi. Okay. I am Angeles Casas. I am a remote sensing data scientist in the Climate Corporation. For those that didn't hear yesterday, it's a company that the main goal is to optimize the productivity of the grower in a sustainable way. And for that, we provide recommendations, or we provide the tools so the grower can take informed decisions. I drive the effort of modeling the environmental conditions of the cropland. So for that, we have several machine learning frameworks using to characterize the soil of the environment. And for that, we need remote sensing and other geospatial data, right? So the interest in ARD is actually this idea of ARD as an API functionality where I can get in a standardized way, what is it that I have when I am given this remote sensing data, if it's harmonized or whatever data set it is. I want to know the provenance, the versioning of it, and the errors, as we have been talking about. But even more, I would like to know how those errors were calculated and in what specific process to get to that ARD. And just be informed about those so I can take an informed decision when I decide if I want to include those into my, as a features into my machine learning ARD, right?
Hello, everybody. My name is George. I am the Chief Technology Officer of Atlas AI, which is a very small local startup. In fact, we're actually just a few blocks down the street. The mission of the company is to provide geospatial analytics with the specific goal of informing the sustainable development goals. So anything that goes from agriculture, productivity, to some socioeconomic indicators. So we try to sort of come up with insights across those verticals. And our daily routines include, obviously, remote sensing and in combination with survey and ground data, and which we feed to AI pipelines to generate these insights. We are deeply rooted in academia. In fact, we were an academic group until last year at Stanford. We decided to spin off the startup to sort of go from the proof of concept sort of researchy aspect of this work to a more large scale, distributable, usable product that can actually be deployed.
Thank you, George. So one of the things that I've seen, having talked to the panelists before we actually came up here, and also talking to a few of you in the past, prior to ARD being like a more annual event, there have been largely these two communities, the communities of remote sensing experts, very familiar with the domain, and the community of computer vision practitioners and machine learning experts, very familiar with algorithms in that domain. And this community brings together, this is the kind of forum where we're bringing together these two communities. So I want to start with one of the topics which is relevant, time series analysis. So most folks who, most computer vision and machine learning practitioners are enamored by the capabilities in remote sensing with the expectation of a deep stack across time of like pure imagery where pixels have very accurate values. And soon as we start working with it, we end up realizing that going with the 80-20 Pareto, we spend 80% of our time really data munging and getting it to a form where we can spend a time training and inferring on models. So with that end, I wanted to start with like the most treasured and celebrated use case, which is time series analysis towards NDVI. We had a handful of presentations earlier today around that. So I wanted to channel this conversation to both Rinkal and Angeles around how did those presentations resonate with you, and where do you see the gaps, the opportunities and the challenges between what exists today, the methodologies you saw, and what you would like to do with ARD in the future?
Well, I can start. Well, as I mentioned, I want to dedicate my time to the model to generate the value added, right? So I really don't want to spend any time here. That's why my interest is in just I want to know exactly how things happen so I can use them. So very excited about all the talks here. I could totally use all the harmonized data sets. They are tremendously interesting to me. So the gap is a description of those, right, in the stack or the ARD. What are those errors? How can I compare them? And actually, if all these harmonizations on all these data sets that are provided, even if they could calculate the error from a common data set, then that would be even more helpful to me. But the fact that they are already providing it's tremendously exciting. It increased the temporal frequency, so therefore the analysis that I can do with it. So still the gap would be a proper definition of the stack, so I can use them in an informed way. So the gap is the same, I would say. I think the opportunity is huge because I want to, following the line of the talk that my colleague Ali Reza did this morning, that the whole process can be really heavy. Actually, it could be 90% of the whole. And then the 10% is the actual machine learning model. The preparation is the heavy part. If you can actually bypass the concept of the pipeline, and you can actually have a way, because you have that stack, a way to query exactly what you want, and actually just bring like an on-demand service. What is it that I want? Because I exactly know what it is for a specific use case. And then in the same way that he showed, actually he just showed how to calculate the NDVI, but actually you can go even further and clean it, do all the processing that you might have, particularly if it's already corrected, and then maybe even go through the transformation and the grid alignment that you need for your machine learning. So that's the opportunity when data is so well characterized and it's so easy to search and to identify. It should be, there are tools that we can exploit to create this machine learning ARD in the same way. You can describe the workflow, but you can have the flexibility to have it for your specific use case. But then, of course, the challenge is, well, first of all, doing it, having everything together, and then in the case of climate, the challenge is yet one more part, which is actually when do you match this part with the ground truth or the label or whatever you want to call. In our case, that data set is also, of course, spatially distributed, but sometimes it's in the shape of points. Sometimes it's spatially distributed, but not exactly in the same raster format. So the challenge, again, is how do you make the transformation in a way that you're preserving the quality of both sides of your remote sensing and actually the ground truth. So plenty of challenges, a lot of opportunities, I would say.
Thanks.
So, yeah, I will address the question with respect to time series analysis. So I think before I address the question, I'll give a brief background about the company that we represent. Myself, I'm part of Corteva Agri-Sciences. That's a large agriculture organization. And I think Angeles represents the BAS of that side of it. So together, we have access to almost 90% of agriculture area in North America, Brazil, and other countries in the world. And imagine every farmer you're trying to connect digitally, and you have access to serve them. And the primary means for us to serve the farmer is through remote sensing from a digital solution standpoint. What can we do best having access to this data? Because we have the ability to connect to those farmers. Time series analysis is one of the most important component. Like if you can monitor simple stuff, very simple, without going into complications of the ARD STAC and everything, but if you can reliably monitor NDVI at a pixel level throughout the time, imagine what kind of questions you can answer. You can understand when the crop is emerging, for example, you can model it to evapotranspiration when the drought onset is happening. You can understand the nitrogen stress aspect. If there is a big infestation through pest, disease, anything, you can understand the effect of canopy degradation or saturation around that time. You can do yield estimation around that time. All those questions that are useful for a farmer in decision making, it can be useful from an NDVI analysis standpoint. And I think as far as historically last 3 years, everything that we are using with MODIS time series analysis, if you can reliably do at planet level resolution, it will be extremely useful. At 3 meter or even sub-meter resolution, if we can do that thing as a community, from a grower facing standpoint, the applications are extremely useful. And the other thing, from a reliable time series analysis standpoint, whatever models that we design in, for example, North America at a pixel level, if we can translate those models in Brazil, Argentina, India, Africa, China in a consistent way, it can help significantly as a community itself. So those are the interesting applications we can leverage on.
So on that note, as you transition from band math-oriented metrics to more sophisticated deep learning powered algorithms that are tracking objects or like features extracted from imagery over time, do you have some examples that you've seen in your realm of expertise which are gaining traction and could use ARD?
Yeah, I think, yeah, so we are dealing with all kind of problems. I think over the last 3 years, having access to a lot of satellite imagery over the last 3 years and also a lot of planet imagery over the last several years. For example, this year we are evaluating from computer vision standpoint the likelihood of ponding areas in a field. If you follow Midwest agriculture this year, a lot of flooding and a lot of issues in Midwest, and growers have issues with that. And using high resolution imagery and some computer vision approach, we are trying to understand the likelihood area where there is a ponding happening in the farm. That is number one. The second thing, understanding field boundaries, is another important component in any digital agricultural discipline. Detecting silos in the field and understanding some kind of mechanical damage and other issues. Those are the other things we are leveraging deep learning, computer vision to detect stuff using remote sensing data. With respect to that, having a good calibrated cross-sensor calibration is important because we are relying on Sentinel-2 data for some as a raw data. Having planet data and other sources aligned to Sentinel-2 spectral response curve, it's very important for us to translate models from Sentinel-based model to planet-based model and Landsat-based model.
Any thoughts from the others related to this?
It's kind of related, kind of not. So it's on the topic of big gaps, basically, and what is missing in the machine learning space for Earth observation. I mean, we talk about bias in machine learning in other fields a lot, but not necessarily that much in the remote sensing field. I think we all know, okay, machine learning learns from training data. So how can we assess the quality of our training data? How can we make sure the data is representative, both geographically, temporally, and also given the topic, whether it's crop, whether it's buildings, whether it's roads, or any other indicator we are looking for, how can we assess that quality and make sure the model is now applicable to a broader region? I think we need to identify that representativeness as a community, how we want to go assess that. I think for smaller scale, in terms of spatial scale applications, that may be not of a concern, but when we want to use all of these data at global scale, at continental scale, we need to make sure our training data has that diversity and representativeness, and that's something I think it's a big gap currently in the community.
So I wanted to transition to another related topic. So we had like a great presentation from our friends at Azzari earlier this afternoon in terms of platform level capabilities to support analysis ready data, to enable analysis from folks like we have on the panel. So I wanted to better understand what kind of platform level capabilities are people building and what are the essential attributes, the highly desirables when it comes to consuming these kind of derived products and semi-derived products and related operations, because it seems prevalent in this community the notion that analysis ready data means different things for different people who are doing different kinds of analyses. So how could platforms in the future enable that, and what are the building blocks towards that kind of capability? I wanted to channel this to Joachim.
Well, it's really getting the basics right. So what you need when you work with data is to get an idea where the data is and what you need. So we're talking of catalogs. So you need an entry point for this. And then when accessing the data, it should be fast, I guess. So if it's on an object store, the file format should be in a way also like COG, for example. So this would be the optimum case, although that's not always realistic, unfortunately. Because the better the foundation is, the better all of the applications are that build upon that. Yeah, that's the main points to me.
Yeah. So more from the perspective of the ESA DASs, where the goal is to enable the friction-free access of both data and information services, which are connected to Sentinel more likely and possible. Are you seeing some early movers with some early wins that are making platform level capability in ARD more less friction, making it easy for them to access?
Yeah, I mean, what we attempt is, so with our EX Cloudless product, is to address customers who don't really care from which date the pixel values come from exactly. So they just provide a time frame, and then they just say, yeah, we want a full data coverage over our AOI, and they don't care of internal tiling or how the whole data set is organized. I'm going to have a slide on this on my presentation tomorrow, because the Sentinel data, for example, it's being recorded in data takes, but then it's chipped up into overlapping tiles. And when you simply ask a catalog, give me over this location every product you have, then you can get multiple files containing basically the same data. So this is also an abstraction level we could provide to the customers, because I guess machine learning companies don't want to work on this as well. So I think this could also be so on the if you imagine ARD being a spectrum of what people could want, then this is certainly a point to address. So on one end of this spectrum, so to disseminate some standardized tiles or chunks of data.
Yeah, so we did hear a few different systems being used around the military-grade reference system. There are some systems that are tiling across UTM grids. So how does a platform like what you're designing handle that kind of tiling mechanism? Do you serve one? Do you think about a flexible way to serve it in whichever form you want?
Well, yeah, we're flexible in a way that we can decide which grid we want to deliver our tiles. Our standard product uses the lat-long grid. It bases on the WMTS on a certain zoom level. So when we process data, so we build temporary time cubes, and there we don't have any information on the single granules anymore, because we aggregate them to the data takes. And yeah, that's an approach that could be done. Yeah, for this.
Definitely.
Yeah.
So on a different topic, one of the and I'm switching between a few different topics, and this is probably the last couple before we open out to wider audience Q&A. So one of the big promise of having this rich set of data with a growing number of catalogs is the potential for social impact. So over the last several years, world bodies like the World Bank and the UN have been looking to Earth observation data and remote sensing imagery as like a source towards data-driven pursuits for social development. Amongst us, we have someone who's been actively looking at that. So I want to turn the conversation to you, George, around what are some leading indicators of systems like ARD being able to help in that pursuit towards attaining the sustainable development goals. So earlier this year, the UN actually released the Earth surface water monitoring portal, where you could see and track the water availability in different regions of the world over the course of time. So we intend to see more of those kind of capabilities being able to targeting social development. So what's your perspective on ARD in that realm?
Yeah, so let's say the quick answer is that it's a whole big mess really out there right now in this social impact domain, and I would draw the line between what's done already so far and what's to be done in the future. And obviously, it's impossible to look at social impact without looking at the past, first of all. And to do that, what you got to do is to look around at what data is being collected already and try to do your best with those data sets, right? And I can tell you for sure that none of them are analysis ready, So very, very messy data sets with huge uncertainties. And what I'm talking about here is mostly big, large-scale surveys from large organizations like the World Bank, other UN agencies, but also local governments. So The good news is that, as you say, the potential of combining Earth observations with artificial intelligence and therefore the need for better training data from surveys, it's pretty quite clear right now. So in the future, there are a lot of agencies and organizations that are going to do a much better job in designing those systems. But looking at the past, there is a lot of work that needs to be done still.
Right.
One of the major uncertainty also is that these measurements, these training data, are points in time and space. And so differently from the more classic machine learning, image-based data sets like ImageNet, they exist regardless of the imagery you want to associate to them, right? So a big challenge here is to figure out what to couple with what. So what data point goes best with what type of imagery. And on top of that, also what characteristic the imagery you're going to leverage for your models.
Right.
And so how to translate that in something that's analysis ready, it's a bit challenging, obviously, because it depends on what type of analysis and applications you are looking for, like many people have said here today.
Yeah, absolutely. So on that note, and you mentioned the magical word, ImageNet. So one of the things we've consistently seen in the last couple of years is the interest in certain organizations, mostly centered around competitions, to release some single source data sets over certain regions which enable computer vision applications. However, they are single source and they are usually around object detection or feature extraction. So what are some of the capabilities that you would like to see towards an ImageNet on Earth observation data in the context of ARD, enabling spatiotemporal analytics?
Yeah, it's a very good question. I think it's still an open one. Hamed and I actually have been working on coming up with a project along these lines. The idea is really to create an ImageNet, something on the same scale really of ImageNet for these kind of applications. What I would like to see mostly, it's really get the basics covered. So first of all, even the simple geospatial accuracy to be a lot better than it was before, than it's been so far really. And then really, I think I would say that the main question here is that we first need to answer it, even before we start thinking about the technical aspects of these data sets, is what are the questions that we want to answer. And until we answer those big questions, we really can't even start thinking about what type of data sets we should collect and how should they look like.
Yeah, so but that's a double-edged sword, right? One can argue that ImageNet is also very, very broadband. It serves a wide variety of potential classes into which you can detect one or classify images. And ImageNet combined with COCO gets you closer there, but they're not specific to domains. But is there the possibility of like building a similar data set that is application or domain neutral, but at the same time derived of temporal stacks that allow foundational capabilities for like a wide range of vertical specific applications? So any other perspectives? I know Hamid, you're smiling, so I know you have something to say.
Yeah, this hits home really hard. Yeah, I agree, it is a tough problem, and I think what we have learned at Radian over the course of at least the 2 years I have been involved with, having one single ImageNet for everything, it's not probably the solution, at least not the short-term one. We can't have what I call a representative data that is addressing all the verticals globally across all times. We need to think about it in a more thematic way. Okay, can we have one potentially for agriculture in a regional sense? Can we have one for land cover, depending on the scale that we are talking, maybe coarse resolution, like 8-class land cover classification at some regional level. For example, a good example of that is the big EarthNet dataset that came out about a couple of months ago, and they presented it at IGARS last week, which is the land cover classification across Europe. It's more of an image classification than pixel classification, but there's no notion of time series. Okay, so something is missing again. But we can build on that. I mean, that's a good starting point. So now we can add Sentinel-1 to that. Now we can add time series to that. So we can go from there, but starting with a one data set for everything globally, I think would be potentially a failure. Let's not do that. But there are many more low-hanging fruits that we can do. And then build pre-trained models. I think the example of the ImageNet is a good thing, that there are a lot of pre-trained models on ImageNet that even now people adopt it and use it with RGB imagery from satellite imagery to, for example, detect ships. We can have more of those fine-tuned to multispectral data, take advantage of all the rich spectral information we have and use that. That's on the data. I want to mention one opportunity because we are talking about the social impact here. And I think part of it is engaging local expert. I think we miss that opportunity always. When we talk about social impact, yeah, the technology is one side of it, but the local knowledge and the context is something we always miss. I very much like the presentation by Sat Intelligence mentioning that you guys go in country and learn what is happening. That is really the key part here. I mean, all of us, I think, are from the developed world in this room. So it is hard to think about the problems there. But yeah, remote sensing can answer that, but it needs an engagement with the local expert as well.
Thank you. Yeah, any other thoughts related to that? Data sets using ARD?
Yeah, I think also just want to highlight there might be opportunities for example, I'll talk from an ag domain perspective, collaborating with companies who have a presence in a lot of countries across the world. Any guidance from this community with respect to the ground sensor network or any other calibration instrument placement that is aligned to agricultural calibration that will help generate proper ARD and STAC products. That is, we are open to engage in those kind of discussions as well. So,
definitely. So one last question before we hand it off to the audience to ask. Any specific resources in the context of machine learning on remote sensing and remote sensing in the context of time series, classification in terms of object detection that you would like to point the audience to in case they wanted to research, look at this further? Come on, folks. There's got to be some reference you have in your mind. Yeah.
There was a lot of them that mentioned in the last day and a half, I think. I mean, the Big EarthNet was one of them I mentioned. The Deep Globe and Earth Vision workshops that the IEEE GRSS organized. There's a lot of good training data sets there and a lot of models, all open source and developed. SpaceNet dataset and the models again developed out of the 4 challenges they have organized so far. It's a good reference thing. There are good training datasets out of ESA, European Space Agency. The Microsoft Earth and AI, AI for Earth program. They are generating some good training datasets these days. One of them is from the Chesapeake Bay kind of mapping. It's actually a concept of an ARD. So they have NAPE data, Landsat data mapped to NAPE, so they have done some sort of a downscaling of Landsat to NAPE resolution, and then labels from the land cover classification, as well as building labels from the Bing project. So it's a kind of a tonsor data, multispectral, all stacked together, ready to use ML ready. That's what we call ML ready data. So as a user, you just go and say, import data, the next step is building your model. So in one line, you have your data. The data is zipped, okay, that's not good. But we are putting it in the cloud soon, and then you can consume it more easily. But those are, I think, good examples that exist in the community. Probably I'm missing a lot of more of those, but these come to my mind now.
Yeah, I'll mention a couple of others. So in the context of competitions, we've had 3 fairly big competitions in the context of machine learning and CV applications on geospatial data or imagery. And those are the Earth Vision conference that was a part of CVPR this year, the Deep Globe competition as part of CVPR last year, and then the SpaceNet Challenge, which is in its 3rd iteration. And we have a few folks from In-Q-Tel, so if you had some questions on this, probably Siegfried from In-Q-Tel, who's here, or Cosmic, can tell you more. So those 3 data sets for sure. In addition to that, there have been a few relevant publications. So XView is one data set that is largely based on world view imagery, and the functional mapping of the world on time series-based classification of land cover, interesting references. So with that, I wanted to open it out to the audience. Any questions that anyone has? Did that all make perfect sense?
I want to say one thing about the data set, if I may. I just want to say that it's very nice that we have so many data sets and that they're ready, but honestly, by the time that they are ready, they stop being useful for many applications. So I still want to claim the flexibility as the most important part of having all the data, and then also in having publicly available data that's again, awesome having that data set. But again, if this data set doesn't have a good way to standardize the information, if I don't know, if I have a wonderful data set, for instance, I work a lot with soil data, and we have a phenomenal data set internally. We have more than 1.5 million points. But we also want to use publicly available data of organic carbon content or anything. If I don't know, if that data is not collected with enough metadata, I don't know what I'm doing. I don't know what I'm putting into my algorithm. So again, going back to STACs and ARD, it's a fundamental part to document everything, to have access to this metadata in a standardized way. So I can easily, I can filter what I need. It's not that I need a perfect data set. I can account for errors in the data set. I might put them in my training data set, but not in my validation. I think just the information about how the quality, what is the quality, how it was collected, what is it that all the transformation that can happen. So sometimes you have the data, but you need to be careful with all the processing that you do, because it's clear that we have to do from the remote sensing and from the label again. And these transformations need to come from the use case and all these decisions. If we don't have flexible enough ways to create these machine learning ARDs, if we don't have information about what is the data or what happened to that data before we put them, we don't have control upon what we're doing, and then we are introducing those errors in the downstream, and we are not accounting for the propagation of those errors. We are accounting for perfect measurements and perfect data, which is not the case. So our models end up being worse.
Yeah, definitely. Any other topics? Great, all right. Ignacio, fire away.
Yeah, I mean, I guess the counterpoint that I wanted to make is if you have to include a lot of metadata that tells you how the data was generated, then the data is not really ready for analysis. And I would argue, right? So part of our job is to make that need, to obsolete that need, because the data contains at least error bars that we all agree how they're measured. And I don't know.
Are you talking about the remote sensing data, the remote sensing part of things?
Yeah, well, as a scientist, right, for any instrument you build, when people start asking what's going on under the hood inside your instrument, it's because the instrument is perceived as not being working, right? So then how do we address it?
Yeah, I just need information about what are the processing that happened to that. I don't need every information, but maybe some that are relevant for me, that give me enough control on the decision of which one to use. So for instance, if I have an harmonized data set, what is the error in the georeference? There must be use case in which I can afford to have, to link a point to my pixel, or because it's about the same, it doesn't change that much in space. So I want to know what is that error and take that decision, or I can get this data set. But for another application, I absolutely don't want an inconsistent atmospheric correction. So if you tell me, we have this data here, we corrected with this algorithm and this one with this other, I just want to know, when I talk about metadata, I mean some sort of standards, some basics of how things happened that help me take the decisions. In some cases I will choose some, in some cases another one. But I know that overwhelmingly amount of metadata doesn't help anybody.
Yeah, well, it gets in the way of standardization because then every instrument will have its own quirky metadata. So I think the ultimate metadata comes from statistical estimation, right? If we could distribute an estimated probability distribution, right, for every single value that is on the data sheet, then go beyond the variance and the error, actually a distribution. And yeah, you will get some values that are uniformly distributed, meaning you just don't know the value. And some of them are going to be tighter. So like more of a Bayesian approach, and then you can propagate everything. So we could agree that every value you put there comes with a 100-long vector that describes a coarse, low-res PDF for every value. And then you can weight the evidence accordingly in whatever decision you're making, or hopefully automatically.
Hopefully, yeah.
Yeah, please.
What we're talking with, I was just thinking that there is a slightly ironic aspect to this conversation about analysis-ready data and machine learning, which is that sort of in an ideal world, if we really had enough of this data, like it wouldn't matter if they were analysis ready, because you could actually build models that learn to understand the patterns of atmospheric contamination, topographic effect, and whatnot, and just don't care about that part. It's just I thought it was ironic to mention it.
Right. Any other questions? Please.
I have a question. So one of the major things we have to deal when we design payloads to put in space and take pictures is what we bring down. And I think we're forced to bring down rasters because there is an emotional attachment to something that appears to be an image. Even though people take the data and immediately do a few computer vision tasks and spit out features, for example, right? So why am I being asked to download rasters all the way from space and over-engineer the entire system with radios and everything, when in reality all I need is features and vectors with a pinhole camera model, and then descriptors for every point? Why am I not streaming just as the features with a standardized way of describing the features that fits into any computer vision workflow? Why are we still attached to the idea of a raster of an image? I feel it's almost like an emotional attachment. The image doesn't exist. It's a construct in the payload, right? It's subject to optical distortion, atmosphere, all these things. What I really want is a line of sight to a point on the Earth and a descriptor of that point. That's pretty lean. So I would like a standard that describes what is needed for some of the computer vision tasks and machine learning tasks, so I can build to that standard and move all that stuff on orbit. So I only bring down data when there is data in the so-called image or field of view. Does that make sense? I don't know if this is a good, well-formed question.
First thing is that you need, particularly with CubeSats, like hundreds of them, you need calibration. So first, we should solve that problem to be able to do that on the platform, on the payload. If we can do that, then those features that we are talking about, it's so diverse. There is no kind of, even if you think about one application, I don't know, let's call some object detection on the ground. Like, you can't get everybody in the community to agree on one set of features. Okay, these are only the features we need for this type of algorithm. And then if you do that, you're missing a lot of good information that might help you develop better algorithms, right? Because you need to do feature engineering for future algorithms or future kind of machine learning techniques that come up. I know downloading the image from the payload to the ground is really a headache. But it's also a tough problem to come and define those standard features.
Yeah. I mean, look, there is a computer vision task that is happening on every single satellite automatically all the time, which is a multi-view problem where you're establishing correspondence between different bands and realigning them to form this image that doesn't exist, right? This is a hypothetical image because actually the spectral bands are collected from different points in the sensor plane. So the image itself doesn't exist, really. So now you have to construct that. In the process of constructing that, you find all the features in the image, you correspond them between different spectral bands, and align them to make the image. In the process of making the image, you found everything that was interesting in the image, because that's how you band align the imagery, right? So that's it. We are throwing away information. We're compressing the data with algorithms that were fine-tuned in the compression, the decimation tables for pictures of cats and people that we use on the satellite, the same, JPEG 2000 or JPEG, DCT, JPEG, decimation tables that were designed for particular power spectrums of imagery. They're not designed for geodata. We have to retune probably compression for geodata. So we are throwing data away in a probably pretty biased way. Anyways, it's just, can we do it in a controlled way, right? And can we do it on orbit, ideally?
It's a good question, Ignacio. I think the challenge to deal with so much, for example, planet data in-house is tremendous. It is expensive as well. I think going back to Hamid's comment of if the satellites are designed with particular domain in mind, for example, out of 100, 200 satellites, you were launching 50 satellites focused for agriculture application, all I care about is an IR and other band and some derived information based on that. and downlinking that data for that particular application can be interesting. I think the challenge right now is I'm assuming Planet has all these different, or other CubeSat companies has these different verticals they want to serve. That's why downloading raster data makes sense, and people consume or extract features that is interest to them. But in future, in 1 or 2 years from now, we would hope those CubeSats can talk with each other, or even with the larger satellites in the space itself, run the analytics over there, and download the derived product back to us. That will save tremendous cloud cost, example.
Well, I mean, one of the trades we can break with distributed constellations is the idea that there has to be, we have this idea that we have to build a SAT that fits all the uses, but our customers are only in a couple of verticals, right? So the SAT already is used only one way, right? So, or a couple of ways. With a disaggregated constellation, you can break that trade because you don't have a single bus that is the size of a bus where you put a couple of payloads. We could build really well to an application, and if a new application comes in, you launch a second constellation to flying alongside, right? So we have an opportunity to break those trades. We have artificially coupled the idea of an image specification of an image into things that are not coupled anymore, because the structure of those buses and the payloads is not really coupled. They're different entities. So, I mean, but we need the buy-in of the community to, from our side, to take the step and say, cut that constellation in half, and have a machine learning sidecar constellation, and have a AgSat and a FireSat, and so on, right? So we cannot do it alone. But for that, we need to let go of the concept of an image together.
Which is, probably there is a state-of-the-art 5 to 10 years from now where those things are in the realm of possible. But there's also an element of, like, every data business that's actually selling data today is looking at downlinked imagery to different levels of processing, to analytics as different data transformation. So one can argue everyone in this room is in that business of doing data transformations. And when you want to serve multiple verticals, there is a minimum viable or lowest common denominator for multiple applications, which is where the state of the art for data is today. And with ARD, we are trying to, like, move that needle a little further downstream to make it more possible in the realm of feature extraction. But I do want to talk about one specific item, and this might be an open area, which is what is the tolerance? Because what's the tolerance for machine learning algorithms, in particular in the context of deep learning today, on how much variability and how much readiness exists in the ARD? Because we have seen some very fascinating examples of feature extraction from mosaics, visual mosaics, analytic mosaics, mosaics built out of Sentinel. So in those cases where people are doing change detection, one can argue there's spatiotemporal analytics happening today with the tools that they have access to today. So it seems like there is some resilience in the deep learning models towards that kind of capability. Do you all have some perspective on that?
I have one comment which is related to that. I mean, the example of change detection, for example. Let's say we have a deep learning algorithm looking at 2 scenes, doing a classification and see if there is a change or not. I think the reason we do it this way is that the typical common machine learning algorithms, as George mentioned, are designed for images, not for time series. We should go and model the change using the deep learning algorithm rather than classifying 2 snapshots and say if there is a change. We should look at the time series and say, is there a change in the time series rather? So the change is basically the target prediction rather than 2 objects and then differencing them. That's the kind of trade-off we should make, or the paradigm shift we should make in our field.
And that's definitely a much larger conversation. So we at Planet definitely care deeply about change detection. There's also the thesis that identifying candidates of change is relatively straightforward. Identifying meaningful change is a very complex problem. And that's where the path towards getting there can get tricky. All right, so are we? Another question?
Hello? Oh, okay. So, I mean, just before everybody goes, we're going to get dinner at Left Bank in Menlo Park. Same place we did last year, great restaurant, so it's already paid for, so please come and eat.
Yeah.
I guess going back to interoperability, we keep talking about interoperability in terms of error bars and radiometry and surface reflectance, so on and so on and so on. What I would like to see as a test for interoperability is a test that allows us to determine in an automated, unattended, unintervene and tamper with, whether or not the training and the models that are used to do inference are portable across platforms. Because what I would like to do is I would like to iterate the CalVal until the machine learning passes the same cross-validation scheme right across to different payloads. Because you could solve for portability, and that local minima of the optimization of how you do CalVal might not be the same one that takes you to the most accurate surface reflectance. There could be variance trade-offs. So the analysis-ready data that is for machine learning, that leads to portable models, might not be the one that gives you the most physically accurate measurements, right? So how do we do that as an industry? I would like to have a place where you can upload your data with labels and swap payloads or simulated data or whatever, and you can stress test and test, did the training of the model break down? Is the model picking up differences between the payloads versus differences in the scenery? Any takers?
I think that's the issue we faced in the past, we're still facing. But it depends on the kind of application. So if you're doing pure time series analysis, modeling of physiological process, for example, transpiration or some other photosynthesis, then it is very important. Then the CalVal process and across payloads and everything should synchronize well. But if you do an object detection kind of thing, pure computer vision kind of thing, I hope it doesn't matter. The covariance between spectral bands, today latest deep learning algorithms captures that, and the relationship between pixels is the one that matters. That from that perspective,